September 7th, 1942. Neville Island, Pittsburgh, Pennsylvania. The champagne bottle swung through the humid afternoon air and shattered against the flat, ungainly bow of LST-1. And for just a moment, the 12,000 workers packed along the riverbank fell silent. They watched this strange vessel, 328 feet of welded steel that looked nothing like a proper ship, slide backward down the ways into the Ohio River. The hull hit the water with a sound like thunder, sending a wave surging toward the opposite bank that forced spectators scrambling up the muddy slope to avoid getting drenched. Standing on the launching platform, Dravo Corporation's chief engineer watched the LST settle into the river and felt his stomach tighten. He knew what the Navy didn't yet understand, what nobody outside his engineering team had quite grasped. This ship, and the 1,000 more like it that would follow, carried a fundamental design flaw that conventional shipbuilding wisdom said would tear them apart the first time they hit a beach at speed. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem wasn't the flat bottom, though every naval architect in America had spent the past year insisting such a design couldn't survive open ocean. It wasn't the massive bow doors, which Navy inspectors predicted would buckle under stress. It was something far more subtle and far more dangerous. It was the welds themselves. Every single one of them. Miles of fusion-welded seams holding together a hull that would flex and twist in ways no ship had ever been asked to endure. And in 1942, American shipbuilders were still learning the hard way that welding a ship wasn't the same as welding a bridge or a building. The lessons were being written in catastrophic failure, one fractured hull at a time. The question nobody could answer yet was whether LST-1 and her sisters would join that grim statistics, or whether the innovations being developed in Pittsburgh's inland shipyards would prove that everything the experts knew about welding ships was wrong. To understand how close the LST program came to failure before a single vessel reached combat, you need to go back 18 months earlier, to a cold January morning in 1941, when a brand new cargo ship split in half while sitting peacefully in calm water. The SS Schenectady had been launched just days before from a Portland, Oregon shipyard. She was one of the new Liberty ships, built entirely by welding instead of traditional riveting to save construction time. On January 16, 1943, with no warning and no apparent cause, a crack suddenly appeared on her deck, propagated the entire length of the ship in seconds, and the Schenectady broke completely in two. The aft section collapsed, spilling fuel oil across the harbour. The forward section tilted drunkenly, held together only by mangled bottom plates. The newsreel footage shocked the nation. Here was tangible proof that America's rush to mass-produce ships had created floating coffins. Investigation teams swarmed the wreck. What they found was worse than simple construction defects. The Schenectady represented a fundamental misunderstanding of how welded steel behaves under stress. Traditional riveted ships had natural weak points where individual plates joined. If a crack started, it would hit a rivet line and stop. The separate plates acted as crack arresters. But welded ships were essentially single monolithic structures. Once a crack started, nothing stopped it from propagating. The welded seams, if improperly executed, became not joints but fracture highways running the length of the vessel. The metallurgical details were arcane, involving hydrogen embrittlement, brittle fracture transition temperatures, and stress concentration factors that even experienced shipbuilders barely understood in the early 1940s. What mattered was the practical result. Between 1942 and 1945, roughly, 1,500 cases of brittle fracture occurred in ship hulls and decks. 3 Liberty ships broke completely in half. Another 19 developed cracks so severe they had to be scrapped. Dozens more limped back to port with fractures that required months of repairs. The Navy's Bureau of Ships understood they had a crisis. They also understood they had no choice but to push forward. German U-boats were sinking cargo vessels faster than America could replace them using traditional construction. The LST program, already behind schedule and desperately needed for the planned invasion of Europe, represented an even greater welding challenge than the Liberty ships. And unlike Liberty ships, which could avoid combat if damaged, LSTs would deliberately drive themselves onto hostile beaches, subjecting their hulls to stresses no cargo vessel ever faced. Admiral Samuel Robinson, chief of the Bureau of Ships, made the situation clear in a classified memo dated February 1942. The success or failure of amphibious operations in both Europe and the Pacific depends absolutely on our ability to land tanks and vehicles directly onto beaches. We currently possess no vessel capable of performing this function reliably. The LST design represents our best solution, but it requires welding techniques and stress calculations beyond our current proven capabilities. Failure is not an option, neither is delay. The LST design itself was a study in contradictions that made conventional naval architects queasy. The ship needed to be ocean-going, capable of crossing the Atlantic or Pacific in all weather. That required a deep draft for stability, but it also needed to drive directly onto beaches, which required a draft shallow enough to clear sandbars and obstacles. The solution was a massive ballast system that could be flooded for ocean passages and pumped dry for beach landings, allowing the ship to reduce its forward draft to less than 4 feet. The hull shape was equally problematic. To distribute weight and prevent the flat-bottomed vessel from digging into sand, the LST had an extremely broad beam relative to its length. The length-to-beam ratio was 6:1, compared to 10:1 for a conventional destroyer. This made the ship more stable when beached, but it also meant the hull would experience torsional stresses, actual twisting forces, far exceeding anything a normal ship endured. When an LST ran down a quartering wave in heavy seas, observers on the bridge could actually watch the hull twist visibly. Vehicles loaded on the weather deck would rise and fall rhythmically as the entire ship flexed like a steel snake. Sailors reported that in extreme conditions, they could look down the length of the tank deck and see the far end shifting several inches side to side relative to the midship section. These torsional stresses concentrated at the welds. Every fusion-welded seam became a potential crack initiation site, and if a crack started in a welded LST hull under these conditions, the consequences would be immediate and catastrophic. The ship would literally peel open like a sardine can, spilling tanks, troops, and crew into the ocean. The man tasked with preventing this disaster was not a formally trained naval architect. John Niedermayer had sketched the basic LST design in a matter of days back in November 1941, working from British requirements and his own understanding of what American shipyards could actually build. His design was brilliant in its simplicity, but Niedermayer had no illusions about the engineering challenges it presented. In March 1942, 3 months before LST-1 would slide down the ways, Niedermayer wrote to Dravo Corporation with unusual candor. The LST design pushes welded construction into uncharted territory. The flat bottom creates stress patterns we cannot fully predict. The bow door assembly represents the largest welded opening ever attempted on a vessel of this size. I cannot guarantee structural integrity under combat conditions. Your fabrication techniques will determine whether these ships survive or fail. Dravo's response came from a man who understood both the problem and the potential solution. Frank Dravo, who'd taken over leadership of the company after his father's death, had spent 2 decades building barges, towboats, and underwater structures on inland rivers. Dravo's welders weren't building elegant ocean liners, they were building workhorses that had to withstand river ice, debris impacts, constant grounding, and years of abuse with minimal maintenance. More importantly, Dravo had pioneered electric arc welding techniques in the late 1920s, when most shipyards still relied entirely on riveting. The company had launched its first all-welded barge hull in 1929. By 1942, Dravo's welding supervisors had accumulated practical knowledge about stress fracture prevention that the Navy's theoretical engineers were only beginning to understand. The challenge was translating that knowledge into procedures that could be executed at scale by largely inexperienced workers. Because that was the other crisis nobody wanted to discuss publicly. The LST program would require training thousands of welders who'd never seen a ship before, let alone welded one, and they'd need to produce work good enough that sailors' lives depended on it. The numbers were staggering. To construct a single LST, Welders would join 23,300 individual pieces of steel, totaling 1,340 tons. Every joint had to meet specifications. Every seam had to be inspected. Any defect could propagate into a catastrophic crack months later, when the ship was in combat thousands of miles from repair facilities. Dravo's training program began in April 1942, with an acknowledgement that contradicted everything traditional shipyards believed. Most jobs at Dravo required 2 weeks of training before workers could contribute to production. Welders received 4 to 6 weeks of intensive instruction, not because the work was more difficult, but because the consequences of failure were absolute. The welding instructor, a man named Kozak who'd learned his trade building pressure vessels for oil refineries, designed the curriculum around a single principle. Forget everything you think you know about welding. Ship hulls are alive. They move. They flex, they twist. Your weld has to be stronger than the surrounding steel, or it becomes the failure point, and you're welding steel that's already under stress from the moment we assemble it. That last point was crucial. Traditional ship construction assembled the hull from the keel upward over months. Each section could settle and adjust as it was added. Dravo's assembly line approach prefabricated entire sections in different locations, then lifted them into place with massive cranes. These sections didn't fit together perfectly. They couldn't. Steel expands and contracts with temperature. The river bottom bedrock wasn't perfectly level. Tolerances accumulated across dozens of prefab modules. So welders weren't just joining steel plates. They were pulling sections into alignment, holding them under tension while making the weld, then moving on while the structure adjusted around their work. The welds had to accommodate those adjustments without cracking. That meant understanding not just how to lay a proper bead, but how the entire structure would behave as it cooled and settled. The traditional approach to ensuring weld quality was visual inspection, followed by X-ray examination of critical joints. This worked fine for small structures or when you had months to complete construction. Dravo was attempting to produce completed LSTs in weeks. There wasn't time for comprehensive X-ray inspection of every weld. They needed a different approach. The solution came from an unexpected source: Chicago Bridge. Iron Company, operating a shipyard in Seneca, Illinois, had built their reputation manufacturing pressurized tanks of various types and shapes. These tanks had to contain fluids and gases at extreme pressures without leaking or failing. CB&I's welders had developed techniques for creating absolutely reliable seams using specific rod chemistries, precise heat control, and multi-pass welding sequences that distributed stress evenly. When CB&I was selected to build LSTs specifically because of their welding reputation, they shared these techniques with other yards in the program. The knowledge transfer happened through a combination of training manuals, visiting supervisors, and something the Navy had never tried before: standardized welding procedures that every yard would follow exactly. The procedures were exhaustive. They specified the type of welding rod down to the chemical composition. They defined the amperage range for different plate thicknesses. They dictated the sequence in which seams should be welded to minimize warping and stress concentration. Most controversially, they required preheating thick sections before welding and specific cool-down procedures afterward. Traditional welders hated these requirements. Preheating took time. Following a rigid sequence meant you couldn't just weld whatever section was convenient. The procedures felt like bureaucratic interference from people who'd never held a torch. But the procedures worked. Once implemented systematically across the program, weld failure rates dropped dramatically. The real innovation wasn't any single technique. It was the recognition that mass-producing complex welded structures required treating welding as a system, not a craft. Every welder had to execute the same procedures. Every supervisor had to inspect using the same criteria. Every deviation had to be documented and corrected immediately. This standardization solved another problem nobody had anticipated. When LSTs inevitably sustained damage in combat, repair teams needed to know exactly how the original structure had been built. With standardized procedures, any shipyard could perform repairs knowing the weld characteristics and stress patterns. Without standardization, each ship would be unique, and field repairs would be guesswork. By the time LST-1 hit the water in September 1942, Dravo had trained over 4,000 welders using these new procedures. The company was completing hull assemblies at a pace that would have seemed impossible a year earlier. Sections that should have taken weeks to fabricate and join were coming together in days, and the welds were holding, but nobody knew if they would hold under combat conditions. That test wouldn't come until August 1943, when LSTs hit the beaches of Sicily in the first large-scale test of these strange, flat-bottomed ships and the miles of welds that held them together. On the morning of July 10, 1943, LST-313 ground onto the beach at Gela, Sicily, with her bow doors yawning open and her ramp extended onto dry sand. Sherman tanks rolled off directly onto Italian soil. German artillery bracketed the beach, sending geysers of sand and shrapnel across the landing zone. Machine gun fire raked the LST's superstructure, and the ship's hull, subjected to violent grounding impact and the stress of high-speed beaching, held together perfectly. Over the next 3 days, LST-313 made 17 round trips between the invasion fleet and the beach, taking damage from near-miss bombs and shell fire, grounding repeatedly on rock and sand, operating in conditions far exceeding design specifications. When inspectors finally examined her hull after the Sicily operation, they found stress fractures in several non-critical locations, but no catastrophic failures. The welds had performed exactly as the standardized procedures predicted. The same pattern held across the invasion fleet. Of the 229 LSTs that participated in Sicily, 3 sustained hull damage severe enough to require shipyard repairs. None broke apart. None developed the kind of catastrophic fractures that were still plaguing Liberty ships. The welding procedures, so painfully developed over the previous year, had proven themselves under the only test that mattered. But Sicily was calm water compared to what would come next: the English Channel in winter, the North Atlantic in storm season, and the ultimate test, Normandy, where over 170 LSTs would drive themselves onto hostile beaches in the largest amphibious assault in human history. The preparations for D-Day revealed just how far American understanding of welded ship construction had advanced in 2 years. Every LST scheduled for the Normandy invasion underwent what the Navy called stress reinforcement modifications. This was bureaucratic language for a brutal truth. The ships would be operating at the edge of their structural limits, and every possible failure point needed additional support. The modifications focused on the areas where stress concentrated most intensely: the hull sides, where the flat bottom transitioned to vertical plating, received welded reinforcement straps. These straps didn't add much structural strength, but they acted as crack arresters. If a fracture started, it would hit the strap and ideally stop before propagating further. The same principle that rivet lines had provided in old-fashioned construction, now implemented through deliberate weak points in welded structures. The bow door assemblies received particular attention. The doors themselves were 14 feet wide, designed to allow passage of virtually any military vehicle. This meant the bow had a massive opening that interrupted the hull's structural continuity. The doors had to seal watertight for ocean crossings, then swing open rapidly on the beach. The hinges and locking mechanisms were potential stress fracture sites. Dravo's engineers had anticipated this. The bow door assembly used a design borrowed from pressure vessel construction, with the doors essentially plugging into the opening rather than simply sealing against it. Hydraulic rams provided the closing force, distributing stress across the entire door perimeter rather than concentrating it at hinges. But this design had never been tested on a ship that deliberately beached itself at full speed. The other concern was thermal stress. Welding adds tremendous heat to steel, and different cooling rates can lock residual stress into the structure. In a static building or bridge, this isn't catastrophic. In a ship hull that flexes constantly, these residual stresses added to operational stresses can exceed the material's limits. Chicago Bridge and Iron's contribution here proved decisive. Their experience with pressure vessel construction had taught them that stress relieving through controlled heating and cooling after welding could eliminate residual stresses. But you can't heat treat an entire ship hull. Instead, CB&I developed localized stress relief techniques, heating specific high-stress zones with special torch arrays, allowing controlled expansion and contraction, then cooling slowly. This process added days to construction time, but it prevented catastrophic failures months later when ships encountered extreme conditions. By early 1944, every LST coming off the production lines underwent stress relief treatment on critical welds before being released to the Navy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The personnel challenge matched the technical challenge. By mid-1944, the 5 cornfield shipyards were employing over 60,000 workers, most of them in welding-related trades. This workforce included large numbers of women who'd entered industrial work in unprecedented numbers as men deployed overseas. At Dravo alone, over 40% of welders were women by 1944. The gender shift required adjustments to training and equipment. Women generally had less upper body strength than male welders, which affected their ability to handle heavy welding equipment for extended periods. But many women proved more meticulous in following the standardized procedures, resulting in lower defect rates. The best welding crews often mixed experienced male supervisors with female welders, combining physical strength for setup with precision execution. The racial integration of shipyard workforces proceeded more quietly, but no less significantly. Northern shipyards like Dravo and CB&I hired black workers in substantial numbers, training them to the same standards as white workers and paying equal wages for equal work. This wasn't altruism, it was desperate necessity. The labor shortage was so severe that excluding any capable workers would have crippled production. Southern observers noted with alarm that integrated shipyard crews in Pittsburgh and Evansville were proving that black and white workers could collaborate effectively on complex technical tasks. This inconvenient fact would resurface after the war when segregationists argued that integration was impractical. The LST program had already demonstrated otherwise, though this lesson was carefully ignored by those who preferred not to learn it. By the spring of 1944, as LSTs gathered in English ports for the Normandy invasion, the ships represented more than just military hardware. They embodied a revolution in manufacturing technique, a transformation of the American workforce, and a solution to engineering problems that conventional wisdom said were unsolvable. The welds holding these ships together had been executed by workers who 18 months earlier didn't know the difference between a TIG torch and a stick electrode. The procedures guiding that work had been developed by engineers translating pressure vessel techniques into shipbuilding. The materials themselves, the welding rods and steel plate, had been refined through painful trial and error to resist brittle fracture in cold seawater. None of this was the work of one person. There was no single genius welder whose forbidden technique saved the program. Instead, it was a collective effort involving thousands of workers, dozens of engineers, and the hard-won knowledge purchased by every fractured Liberty ship and every failed pressure vessel test. But the test still awaited. On June 6, 1944, those welds would face conditions beyond anything experienced in Sicily or training exercises. German artillery, underwater obstacles designed specifically to rip open landing craft hulls, cold North Atlantic water that made steel more brittle, and beaches that would require multiple high-speed groundings in rapid succession. The morning of June 6, 1944 arrived cold and miserable across the English Channel. Winds gusted to 20 knots, waves reached 4 to 6 feet, conditions that would have postponed training exercises. But this was no exercise. Eisenhower had already delayed the invasion 24 hours due to weather. Another postponement might mean weeks of waiting, with the risk of losing tactical surprise entirely. LST-47, built at Dravo's Neville Island yard 11 months earlier, wallowed in the pre-dawn darkness 8 miles off the Normandy coast. Her tank deck carried 18 Sherman tanks, 14 deuce-and-a-half trucks, and a platoon of combat engineers, with enough explosives to clear beach obstacles for a quarter-mile. Her main deck held another 12 vehicles and crates of ammunition stacked so high that the ship's machine gunners could barely see over them. The coxswain, a 23-year-old from Ohio who'd never seen the ocean before joining the Navy, kept his eyes fixed on the dimly lit stern of the LST ahead. The ships were running in column, maintaining precise intervals, heading toward a beach the invasion planners had designated Omaha. Intelligence. Reports suggested moderate defenses. German forces equivalent to maybe a regiment spread across 6 miles of beachfront. The preliminary bombardment would soften them up. Intelligence was wrong, catastrophically, fatally wrong. At 0600 hours, LST-47 increased speed for the final run to the beach. Through the bow doors, already cracked open to reduce opening time, the coxswain could see the coastline emerging from the gloom. Cliffs rising above the waterline, church steeples in villages that intelligence photos had marked as lightly defended, and tracers, thousands of tracers arcing across the beach in patterns so dense they looked like glowing nets. The German 352nd Infantry Division, a full-strength combat unit that intelligence had placed 20 miles inland, was dug into fortified positions along the entire beach. They had machine guns positioned for interlocking fields of fire. They had mortars pre-registered on every approach. They had artillery on the bluffs, with direct line of sight to the waterline, and they had been waiting, ready, for the invasion fleet. LST-47 was 500 yards from the beach when the first German shell hit the water 30 yards off her port bow. The second shell hit closer. The third struck LST-31, 2 ships ahead in the column, directly on the main deck. The explosion tore through ammunition crates, igniting a secondary blast that killed everyone on deck and left the superstructure a shredded ruin. LST-31 lost power, slewed sideways, and ground to a halt in water too deep for her to beach properly. The coxswain on LST-47 pushed the throttles forward. Navy doctrine said approach the beach at controlled speed to avoid hull damage. But Navy doctrine hadn't anticipated running through this much fire. Speed meant survival now. The LST surged forward at 12 knots, her diesel engines screaming, her flat bottom slamming into waves and throwing spray across the bow. At 200 yards, an 88mm shell from a cliff-mounted gun punched completely through the LST's port side just above the waterline, travelled through the tank deck, missing the lead Sherman by 6 feet, and exited through the starboard side without detonating. The shell left 2 ragged holes 3 inches across. Seawater began flooding the tank deck. The coxswain kept his hand on the throttles. 100 yards. 50. The beach materialized through the bow opening, sand churned by explosions, bodies floating in the surf, burning vehicles, and more tracers than anyone had imagined possible. The LST's bottom scraped sand. The engines roared in reverse, then forward, driving the vessel up onto the beach with enough momentum to lift the bow completely clear of the waterline. The ramp dropped with a metallic crash. A Sherman tank, 29 tons of steel and fury, rolled forward, made it 15 feet down the ramp, took a direct hit from a mortar round that killed the crew and left the burning wreck blocking the ramp. Combat engineers swarmed around it, rigged chains, pulled the wreck aside with a half-track. Another Sherman rolled off. Made it to the seawall before German fire turned it into a coffin. LST-47 sat on that beach for 17 minutes, her bow doors open, her ramp extended, taking fire from 3 directions. Shells impacted around her. Machine gun rounds rattled against her hull. A mortar blast close aboard sent shrapnel tearing through the thin plywood sides, wounding 4 crew members. And through it all, the ship continued disgorging vehicles and men. The engineering officer, crouched behind the con, kept waiting for the catastrophic failure, for the hull to crack open under the stress of high-speed beaching, for the welds on the bow doors to give way under vibration and impact, for something, anything, to fail the way the pre-war naval architects had insisted it would. Nothing failed. When the tank deck was finally empty and the last engineer had scrambled off the ramp, LST-47 raised her bow doors, gunned her engines, and pulled herself backward off the beach. The reverse took 90 seconds. Seawater pumped from the tank deck as the ballast system restored trim. The steering responded. The engines maintained power. The ship turned and headed back toward the transport vessels offshore to load more cargo for another run. Over the next 12 hours, LST-47 made 4 round trips to Omaha Beach. Each time, she took more damage. Shell fragments opened a seam in the main deck plating. A near-miss bomb ruptured a ballast tank. Welding on the port bow door hinge area cracked from repeated shock loads. But none of these failures were catastrophic. The hull remained watertight. The structure maintained integrity. The ship kept operating. This was the pattern across the entire LST fleet at Normandy. Out of 173 LSTs that participated in D-Day operations, 14 sustained damage severe enough to require shipyard repairs after the battle. 3 were total losses, abandoned on the beach after sustaining direct hits that killed their crews and started uncontrollable fires. But not one single LST broke apart structurally. Not one suffered catastrophic weld failure that turned the vessel into 2 pieces of scrap metal. Compare this to the Liberty ship experience. During the same period, 11 Liberty ships broke in half or developed cracks so severe they had to be abandoned. The difference wasn't luck, it was engineering. Specifically, it was the welding procedures and stress relief techniques that had been painstakingly developed over the previous 2 years. LST-338, built at Missouri Valley Bridge and Iron in Evansville, Indiana, provided dramatic proof of how well these procedures worked. On D-Day +3, June 9th, LST-338 was approaching Utah Beach when a German mine exploded directly beneath her bow. The blast was powerful enough to lift the front 40 feet of the ship completely out of the water. The bow doors buckled, the forward hull plating deformed. Every weld in the bow assembly experienced shock loading far beyond design limits. The ship should have broken in half. The welded seams should have propagated fractures that split the hull longitudinally. Every piece of conventional wisdom said this vessel was lost. Instead, the bow dropped back into the water, the hull held together, and LST-338 limped toward the beach under her own power. The bow doors wouldn't open properly anymore, but the ship beached successfully, unloaded her cargo through jury-rigged ramps, and withdrew to England for repairs. When inspectors examined LST-338's hull, they found the explanation for her survival. The explosion had initiated microfractures in dozens of welds throughout the bow section, but none of these cracks had propagated beyond a few inches. The stress relief procedures, the careful heat treatment, the multi-pass welding technique, all of it had created a structure that could absorb damage without catastrophic failure. The reinforcement straps welded onto the hull sides had performed exactly as designed. Several had cracked completely through, absorbing energy and preventing fractures from spreading to the main hull plates. This was sacrificial engineering at its finest. Design deliberate weak points that will fail first, protecting the critical structure behind them. The report on LST-338 went back to Dravo, to CB&I in Seneca, to Missouri Valley in Evansville, and to every other shipyard building LSTs. The message was clear: the procedures work. The stress relief works. The reinforcement straps work. Keep building them exactly this way. Don't change anything unless we specifically authorize it. This standardization proved crucial because LST production didn't slow down after D-Day. It accelerated. The Pacific campaign required even more vessels than the European theater. Every island assault, from Saipan to Okinawa, depended on LSTs delivering tanks and supplies directly onto coral beaches that would have destroyed conventional landing craft. The Pacific environment tested the ships differently than Europe. Coral reefs were harder than sand or rock beaches. They abraded hull plating, stressed welds through constant vibration, and created underwater obstacles that could trap or damage vessels. Tropical heat expanded metal structures, working welds through thousands of heating and cooling cycles. Salt water corrosion attacked any imperfection in welds or plate junctions. At Tarawa, in November 1943, LSTs demonstrated their value and their limitations simultaneously. The shallow coral reef extended 500 yards from shore. Larger landing ships grounded out and stuck fast. Higgins boats could skim across the reef, but they couldn't carry the heavy equipment needed to sustain an assault. LSTs, drawing only 3 feet of water when properly ballasted, drove straight over the reef. But crossing that reef exacted a price. The coral scraped the hull bottoms, scoring deep gouges into the steel. Several LSTs developed leaks when coral heads punctured hull plates. The constant grinding vibration fatigued welds throughout the hull structure. After Tarawa, every LST in the assault force required hull inspections and weld repairs before being cleared for the next operation. The repair procedures developed for combat-damaged LSTs became standardized just like the construction procedures. Every major Navy base in the Pacific had mobile welding teams equipped with portable generators, welding equipment, and stockpiles of repair plates and rod. These teams could patch a damaged LST in days, getting the vessel back into service far faster than returning it to a rear-area shipyard. The key was that every welder in these repair teams trained on the same standardized procedures used in construction. When they looked at a damaged weld, they knew exactly how it had been built originally. They knew the rod chemistry, the heat treatment, the stress patterns. They could execute repairs that matched the original strength characteristics, ensuring the repaired section wouldn't become a new weak point. This standardization extended even to replacement parts. Bow door assemblies, ramp mechanisms, hydraulic systems, all of it was interchangeable across the entire LST fleet. If an LST suffered catastrophic damage to her bow doors, repair teams could cannibalize doors from a scrapped vessel and install them in a matter of days. The welded mounting points were identical on every ship, built to the same specifications in the same locations. By mid-1945, as the war in Europe ended and attention shifted entirely to the Pacific, LSTs had become the most successful mass-produced welded vessels in human history. Over 1,050 ships built, millions of tons of cargo delivered, hundreds of thousands of troops landed directly onto hostile beaches, and a failure rate far below what anyone had predicted when the program began. The statistical evidence was overwhelming. Of the 1,051 LSTs built during the war, 133 were converted to auxiliary vessels, meaning they were sound enough structurally to be completely reconfigured for different missions. 26 were lost in combat to enemy action, and 13 were lost to various causes, including storms and accidents. That's a combat loss rate of 2.5% and a total loss rate of 3.7%. Compare this to the Liberty ship program, where approximately 200 ships out of 2,700 built suffered serious structural damage from welding failures, a damage rate of 7.4%. And Liberty ships operated in the relatively benign environment of cargo transport, without deliberately beaching themselves or absorbing direct fire. The LST success rate becomes even more remarkable when you consider the operating conditions. These ships were designed for single-use, assault operations. Navy planners initially expected to lose 30 to 40% of any LST assault force just from normal combat attrition. The vessels would beach, unload, and potentially be destroyed or abandoned. They were considered expendable. Instead, individual LSTs served through multiple campaigns, making dozens of assault landings, absorbing battle damage, undergoing field repairs, and continuing to operate. LST 388, built at Dravo's Neville Island yard, participated in the invasion of Sicily, Salerno, Anzio, and Normandy in Europe, then was transferred to the Pacific, where she served at Iwo Jima and Okinawa. 6 major assaults, hundreds of beach landings, 5 battle stars, and when the war ended, LST 388 was still operational, her hull intact, her welds sound. This durability was no accident. It was the direct result of welding procedures that had been refined through bitter experience and implemented with religious consistency. Every welder understood that lives depended on their work. Every supervisor knew that a defective weld overlooked today might kill a shipload of soldiers 6 months hence. The pressure was immense, but the system worked. The human cost of developing this system often gets forgotten in the celebration of technical achievement. Workers died in shipyard accidents at an appalling rate. The rush to meet production quotas, the pressure to work faster, the use of inexperienced personnel, all of it created conditions where accidents were frequent and often fatal. Official records list 371 deaths in shipyard accidents during the war years at the 5 major LST construction facilities. Those are the official numbers. They don't include injuries that led to death months or years later from causes like asbestos exposure, which was endemic in shipbuilding. Every LST contained tons of asbestos insulation. Welders working in enclosed spaces breathed asbestos fibers daily. The cancer time bomb wouldn't detonate for decades, long after the war was forgotten, and the men who built these ships had been discarded by the same government that depended on their work. The women who welded LSTs faced additional challenges beyond the physical dangers. They were paid less than men for the same work at many yards, though companies like Dravo eventually equalized wages under government pressure. They faced sexual harassment that was considered normal and acceptable in 1940s workplace culture. They were expected to return to domestic roles when the war ended, their skills and contributions dismissed as temporary emergency measures. But while the war lasted, they proved beyond any doubt that welding was not inherently male work. The best welding crews often had women executing the actual welding, while men handled the heavy materials and setup work. The defect rates from female welders were consistently lower than from male welders at most yards. This wasn't biology. It was attention to detail and willingness to follow procedures exactly rather than relying on improvisation. The integrated workforces at northern shipyards told a similar story. Black welders performed at the same level as white welders when given the same training and treated with the same expectations. The notion that racial segregation was necessary for industrial efficiency was thoroughly debunked by yards like Dravo and CB&I, though this lesson was carefully ignored by those who found it inconvenient. When the war ended in August 1945, the LST program shut down with brutal efficiency. Remaining construction contracts were cancelled. Shipyards began laying off workers by the thousands. Within 6 months, Dravo's workforce dropped from 25,000 to under 2,000. CB&I's Seneca yard, which had employed over 6,000 at peak production, closed entirely. The massive infrastructure built to construct LSTs was dismantled, sold for scrap, or converted to other uses. The workers scattered. Some found jobs in the booming post-war economy. Others struggled as defense industries contracted. The women who'd proved their capability as welders were told to go home, make way for returning servicemen. Many of the skills they'd developed, the precision and discipline required for critical welding work, had no obvious application in peacetime manufacturing. The ships themselves had more varied fates. Over 400 LSTs remained in Navy service after the war, though most were mothballed by the early 1950s. Some were converted to specialized roles. LST 1156 became a repair ship, her tank deck converted to machine shops, and her crew trained to repair other vessels. LST 399 was converted to a mine recovery vessel, hunting for and retrieving unexploded mines along the California coast. Many LSTs were transferred to Allied nations. Britain received 115 LSTs under Lend-Lease and kept most of them after the war. France, Greece, Taiwan, the Philippines, and other countries operated former US LSTs for decades. The ships were simple enough that nations with limited technical infrastructure could maintain them, and versatile enough to serve roles far beyond their original combat purpose. Some became commercial ferries. Several LSTs were purchased by shipping companies and converted to cargo or vehicle ferries. The bow door configuration that made them ideal for beach assaults also made them excellent for roll-on, roll-off cargo service. A few are still operating today in this capacity, 80 years after their construction, a testament to structural durability that far exceeded design expectations. The technical legacy of the LST program shaped shipbuilding practices for decades. The welding procedures developed under desperate wartime pressure became industry standards. The stress relief techniques pioneered at CB&I and Dravo were adopted for commercial construction. The recognition that welding required systematic training, rather than informal apprenticeship, transformed how shipyards developed their workforce. More broadly, the LST program demonstrated that mass production of complex welded structures was possible with proper procedures and quality control. This lesson applied to far more than ships. Post-war construction of bridges, buildings, pipelines, pressure vessels, all of it benefited from the knowledge gained building LSTs under impossible time pressure. The program also validated modular construction and prefabrication techniques. Instead of building each ship from the keel up, yards like Dravo constructed entire hull sections in parallel, then assembled them rapidly. This approach cut construction time from months to weeks. After the war, this methodology spread to industries from housing to aircraft manufacturing, but perhaps the most important legacy was the proof that civilian industries could solve military problems faster and more effectively than military bureaucracies. The Navy's Bureau of Ships had struggled for 20 years to develop effective landing craft. When they handed the problem to civilian shipbuilders, with expertise in related fields, solutions emerged in months. This wasn't because civilians were smarter than military engineers. It was because civilian companies faced competitive pressure to innovate constantly, while military bureaucracies rewarded cautious adherence to proven methods. Dravo and CB&I brought shipbuilding techniques from commercial barge and pressure vessel construction precisely because they weren't constrained by naval tradition. The post-war military-industrial complex institutionalized this relationship between military requirements and civilian innovation. But something was lost in the process. The desperate urgency of wartime, which forced rapid experimentation and brutal honesty about what worked and what didn't, gave way to peacetime procurement processes that valued political considerations over technical excellence. Today, a handful of LSTs survive as museum ships. LST 325, built at Evansville, Indiana in 1942, is preserved in fully operational condition. Visitors can walk her tank deck, examine her bow doors, and see the welded seams that hold the structure together. What they can't see is the extraordinary effort that went into developing the procedures that made those welds reliable. They can't see the thousands of workers who built her, many of whom never saw the ocean before contributing to naval construction. They can't see the engineers who translated pressure vessel techniques into shipbuilding practice. They can't see the women welders who proved gender was irrelevant to technical competence. They can't see the black workers who demonstrated that integrated workforces could meet the most demanding production schedules. What they see is a ship. Ugly, ungainly, functional, a floating steel box with a flat bottom and doors on the front. It doesn't look like an engineering triumph. It looks like exactly what it is: a tool designed to do a job, built with brutal efficiency, and proven in combat under conditions that would have destroyed anything less robust. The welds holding LST 325 together were executed 72 years ago by workers who learned their trade in a matter of weeks. Those welds have survived decades of stress, corrosion, temperature cycling, and the general abuse that comes with being a museum ship operated by volunteers. They're still sound, still doing their job, still testament to the procedures that made mass-produced, complex, welded structures possible. The Navy maintained a fleet of LSTs through the 1990s. The last one, USS Frederick, decommissioned in 2002. By then, the ships were considered hopelessly obsolete. Modern amphibious vessels are faster, more capable, more sophisticated. They're also vastly more expensive, more complex, and more difficult to maintain. Nobody builds ships like LSTs anymore. The simplicity, the standardization, the focus on doing one job extremely well, all of it runs counter to modern military procurement philosophy. Today's ships are multi-mission platforms loaded with electronics and weapons systems, built in small numbers at enormous cost. They're impressive. They're also fragile in ways that LSTs never were. There's an argument to be made that the military would benefit from rediscovering the LST philosophy. Build simple, robust platforms. Make them cheap enough to produce in quantity. Design them to take damage and keep operating. Focus on the mission rather than on incorporating every possible capability. use commercial construction techniques rather than inventing military-specific methods. That argument goes nowhere. The defense industry today depends on complexity. Simplicity doesn't generate the profit margins that sustain modern defense contractors. The political coalition that supports military spending wants jobs and contracts spread across many districts, which requires complex programs that can't be concentrated in a handful of shipyards. So we remember the LSTs as artifacts of a different era, a time when America faced an existential threat and responded by transforming its industrial base in ways that seemed impossible. When civilian companies solved military problems by bringing fresh perspectives, unencumbered by tradition. When welders who'd never seen a ship before proved they could build vessels that would change the course of history. The welds that made it all possible weren't magic. They weren't the work of one genius with a forbidden technique. They were systematic, standardized, carefully developed procedures executed by thousands of workers who understood their work mattered. That's not as dramatic a story as the myth of the lone innovator, but it's the truth, and in its own way, it's more impressive. Because what the LST program proved is that normal people, given proper training and procedures, can accomplish extraordinary things. The welders building these ships weren't heroes, they were working-class Americans doing a job. But they did that job with precision and discipline that made the difference between victory and defeat. Their work literally held the ships together that carried Allied forces to victory. The procedures they followed were developed through painful trial and error, purchased with the Liberty ships that broke in half and the pressure vessels that failed catastrophically. Every successful LST weld represented lessons learned from previous failures. Every standardized technique incorporated knowledge gained through bitter experience. That knowledge didn't disappear when the shipyards closed. It spread through the engineering community, informing how industries approached welded construction in countless applications. The next time you cross a welded steel bridge or drive through a pipeline construction zone or board a ship, you're benefiting from lessons learned building LSTs under desperate wartime pressure. And if you ever find yourself on LST 3, 2, 5 or another museum ship, take a moment to look at the welds. Really look at them. Those beads of fused metal, often rough and utilitarian, represent a revolution in manufacturing. They're the physical embodiment of procedures that made mass production of complex structures possible. They're the work of people whose names we don't know, who changed the world without ever receiving credit. The story of how LSTs beached at full speed without breaking apart isn't about one welder's forbidden technique. It's about systematic innovation, careful testing, standardized procedures, and thousands of workers executing those procedures with the knowledge that lives depended on their precision. It's about transforming an industry in months rather than years because failure wasn't an option. It's about the ugly, unglamorous work that actually wins wars. Not the dramatic battles or the brilliant strategies, but the welding, rods and procedure manuals and training programs that made sure the ships holding the armies simply didn't fail when everything depended on them. That's not the story Hollywood tells, but it's the story that matters, and it's the story that a handful of museum ships still tell, if you know how to listen to what the welds are saying. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.